Alrighty, so on to 3-4. We're going to look at linear inequalities now in two variables. So we talked about how to graph and work with solutions in linear equations with an equal sign. So now we're going to talk about how do we work with inequalities. So our essential questions today, we're going to talk about how do we graph them. So what is the physical, what does that mean? What does it look like? We're going to talk about intersection and union. So going back to like ands and ors, back from looking at overlap and taking everything. So we're going to look at intersection union again, what that means. And then we'll start probably dealing with graphing calculator in a little bit once we have the basic ideas down here. So we'll talk about what these things look like. So the idea of a inequality is that there's going to be not just the solutions that could potentially be on the actual line itself, but the values that are either above or below that line will also be included. So when you think about the difference between having like x equals 7, that's just the value 7. X is greater than 7, for example, in inequality, it's not just 7, it's all the numbers that are, or actually it's not even 7, we'll say greater than or equal to, it's not just 7, it's everything bigger than 7 as well, 7.1, 8, 25 million, anything bigger. So we have this idea of infinitely many solutions that would be going on, but we're going to deal with that in a linear situation, looking at those lines. So we really kind of have basically a three-step process here. The first step, the first thing we want to look at is you want to graph the actual boundary line. We call it a boundary because the graph is going to go up to that location. So kind of like you think about like the boundaries of your yard would be like the edge of your yard, like where you'd put a fence. So it's a good way to kind of think of it as kind of like a fence. It's either going to be a solid line or a dashed line. How do we tell solid or dash? Well, it has to do with whether or not the line is part of your answer, included or not. If the line is included as part of the solution, then you're going to be using a solid lines to fill that in. So that would be when you have inequalities. Think about what you'd have for graphing, even just like the difference between graphing x is greater than 7 versus x is greater than or equal to 7. What would be the difference there? Well, 7 is actually included in this. So if you have greater than or equal to or less than or equal to, that value is actually part of the solution. So you use a solid to show that. Just like you would in a number line, you'd be doing a solid point at 7 and being able to show that versus an open circle at 7, which would not include that value as part of your answer. And that's the same thing with a solid or dashed line. So dashed line would happen when you have strictly greater than or less than. So the solid part, the solid inequalities when the line is included as part of your answer. So those points on the line are solutions to the inequality. And then this second situation for the dash, the line is not included as part of your answer. So that's the same as like open circle, closed circle, same idea. Second step, after we've graphed that boundary, then we take and we have to see whether the points above or below, greater or less, are going to be parts of our solution. So, so the easiest way to do that is choosing a test point. So pick a point that's not on the line, because we know what the line's doing. That's what the inequality is telling us. And then we can plug that in or substitute that into the inequality and check and see if it works. 0, 0 is a great test point, so it's really nice to use 0, 0 unless it's on the line itself. So 0, 0 is a good candidate, but you do have to check to see if that's not on the line, because then you can't really use it because you already know what the line is doing. So if it's not on the line itself, then you're great to use 0, 0. Otherwise, just pick a point that uses 0. So just easier to substitute, but you can pick any point in the region. And then your last step then, once you have decided what that inequality tells you where those solutions are, you shade the appropriate region, either above or below. And whether or not your test point works, it still gives you good information. So if you choose a point and it works there, that means you shade in that direction. That means that point and all the other points on that side of the line are true. And so we're going to shade just like you would on a number line. So like how you graph in a number line and you shade to show where all those points are, because there's infinitely many values. You can't possibly list them. It's the same thing here. We're going to be able to shade then what that region is. So if the point works there, great, shade in that direction. Even if the point doesn't work though, that just means you shade in the other direction. So we're going to be using what we know about graphing lines to be able to help us accomplish this. All right, so first of all, let's see if you can tell the difference between this and what we were doing before. No longer do we have equal there, we have a less than or equal to. So what we want to do first is graph that boundary equation. So the first thing I like to do is just write it as an equation and think about what that would mean. So we're going to graph that line. Now, before we forget, what kind of line is that going to be? Well, look at your inequality. It's less than or equal to, which means what kind of line are we going to use, solid or dashed? Well, equal to means it's included, so we're going to use a solid. It's helpful to think about that. You may still forget when you go back to graph, so always go back and double check that. Okay, well, how can we graph x plus y equals 4? Lots of different ways. Some people like to do intercepts, so let's talk about that. If you do intercepts version, that means to find the x-intercept, that's when y is equal to 0. The y-intercept is when x is equal to 0, so you can substitute those in and solve. If I put 0 in for y, I would have x plus 0 equals 4, so it's going to be at 4, or if you'd like to think of it that way, 4, 0. And if I make x equal to 0, that means I'd have 0 plus y equals 4. So that means the y-intercept is also at 4, but the point 0, 4, right, it's on the y-axis. Some people do that. Remember our little table here, put in a 0 for y, put in a 0 for x. Works great. So we have those locations. So I have the point 4, 0, and I have the point 0, 4, and I know that this is a solid because it was equal to. That means all of the points on the line are included as part of your answer. So that would be one way to graph it. Another way to graph, so this is an alternate, so this is an or. You could take this equation and solve for y, put that into slope-intercept form, so you'd subtract the x on each side. So we'd have y equals negative x plus 4. Okay, can you tell me what the slope and y-intercept would be for that line? So the slope, coefficient of the x, remember if there's not a number there, what is that? So that's a 1. So slope is negative 1, and the y-intercept is 4. So remember how you graph that. That means you go up to 4, and you go down 1, 1 to the right, negative slope, down 1, 1 to the right, down 1, 1 to the right, down 1, 1 to the right. You're going to get the exact same line. So this is kind of your preference. We just need to get that boundary line. Think of it kind of like the fence in your yard. It's at the edge. Okay, now how do I know which direction to shade? One of these regions, either above this line to the right, kind of in quadrant 1, so up here, or below this line to the left, or in quadrants like 2, 3, and 4, is going to be the place where all of those points are true. They make the inequality work. Well, how do we know? Well, you test a point. So I'm going to pick a point to be able to tell, does it work or doesn't it work? And then I'll know which way to shade. Now, 0, 0 is a good candidate, like I said. So if it's clearly above or below the line, that's a good one to try. Now, when we test a point, we're testing it back in this original inequality. So 0 plus 0, is that less than or equal to 4? Well, is 0 less than or equal to 4? Is that true or false? That is most definitely true. So what does that mean? That means 0, 0 was a solution to the inequality. That means any other point below that line is also going to be an inequality or a solution to that inequality. So it's this blue line and then all the values below. So there's infinitely many in this region. So the solutions are below the line and it was solid. Now, kind of a nice rule of thumb, another way to be able to tell that it is actually below is by looking at what the inequality looks like. So I'm going to go back and I'm going to take this original inequality, x plus y is less than or equal to 4. And remember how we solved it for the equation to be able to graph? Well, I could still solve it as an inequality to be able to read it as the original inequality solved for y. So it would be y is less than or equal to negative x plus 4. Notice it's y is less than. That means the y's are less than or below. Look at where you shaded. You shaded below. You shaded under. So when you see this inequality as a less than or equal to, or just a less than, it could have just been that as well, that means you're going to be shading below. So guess what it is if it's greater or greater than or equal to? Guess where you'd shade? Above. The points are bigger, the y's are bigger, and that's something that if you notice it, that might be helpful to realize. So if you see a greater than or a greater than or equal to, either one, that means you are shading above the boundary line. Whether it's solid or dashed doesn't matter. If you see a less than or a less than or equal to, that means you are shading below the boundary, but that's only super important. It's only if your inequality is solved for y. That's really important. So you're looking at what the y's are doing. If it's not, then we just have to go ahead and check that point and make sure we're okay. All right, let's go on to another one just to practice kind of that start to finish process here. 3x plus 4y greater than 12. Okay, so first thing I'm going to do is I'm going to go ahead and solve this for y because we can use that for graphing. We could also use intercepts if we wanted, but I'm going to go ahead ahead and solve this inequality for y. So we have that that less than or greater than to look at. So first thing I'm going to do is subtract the 3x. This is just a way to be able to get this graphed. So you can kind of decide what's the easiest way for you to do this. And then plus 12. And then undo the divide, or times by 4 would be divide by 4. Be careful that you divide everything. So the negative 3 by the 4, so negative 3/4 x. And then 12 divided by 4 plus 3. All right, so that means the equation that we're graphing then is y equals negative 3/4 x plus 3. That's the equation that we're going to be graphing. Now, because this is strictly greater than, will it be solid or dashed? Is the line included or not? Well, there's no equal to, so it's going to be dashed. So when I graph this boundary equation, it's going to be dashed. So because I solved it for y, I'm kind of looking at using the slope-intercept version here for graphing. My intercept, y equals mx plus b, remember that would be the 3, and then my slope would be the negative 3/4. So to graph, go ahead and pause the video for a sec. See if you can graph that. All right, so let's see if we can do this okay. So we're going to go up to 3, and then our slope is down 3, 4 to the right, 1, 2, 3, 4. Or I could go up 3, 1, 2, 3, and 4 to the left. You have your decision there, whichever works better. I like to do a few points just to get a little bit easier to graph. We said this was dashed because the points aren't included because it was just greater than. So I'm going to go ahead and do a dash line here. All right. Now, if we come to, is this going to be above or below? So because we solved this for y initially, I want you to take a peek right here. Y is greater than. Y is greater than. Okay, what that means is if you go back to what we just talked about, because it's greater than, we'd be shading above. All right, so my guess is that I'm going to be shading up here. That's where I think it should be based off of the inequality. Let's try a point though and see if we can check it. So I'm going to test 0, 0 again because it's not on the line. So I'm going to test 0, 0 and see what happens. Remember back in this original inequality. So 3 times 0 plus 4 times 0, is that greater than 12? 3 times 0, just 0. 4 times 0, still 0. Is that bigger than 12? Is 0 bigger than 12? True or false? Absolutely 100% false. Okay, well, a lot of people are like, oh, shoot, that it didn't work. I need to do something else. No, what that means is the point below the line didn't work. So where do they work? To the right or above. Every ordered pair above this line should be a solution. And that fits with our idea of greater than. Remember, great or is going to be shaded above. So we have all the points in that region. So if I picked any ordered pair up here and plugged those ordered pair values in for x and y, it'll make it true. So I know that that's going to be a true sentence. All right, so we can graph just single inequalities. And again, you could have instead, for this inequality, you could have done intercepts, right? If you want to get the line graph that way, you could have put in 0 for y, which means it would have been 3x equals 12, so x equals 4. So you would have had 4, 0, which if you look at the graph, that's exactly where it's crossing. And then you could have put in 0 for x. So that would have been 0, so 4y equals 12, so then that would have been 3, and sure enough, it's at 3. If that's an easier way for you to graph that boundary equation, you go for it, whatever you think's easier. A lot of people like to solve for y, like we did, because then they can look at that y is greater, and that's helpful to them. All right, let's talk about ands and ors. What if you have a system of inequalities, so like more than one inequality that you want to graph together? Remember how we did a system of equations, and they would graph and cross at a point? We talked about that. We'll be doing that again in chapter 4. You can do a very similar kind of idea, but with inequalities. So it's going to be looking at where these two overlap. What do they have in common? Or being able to do all of them at the same time. So we're going to talk about what that looks like. So the difference between an and an or. All right, so first of all, let's talk about what we're looking for and. So if I say it's in this and that, that means intersection. So it's graphing the intersection of the two. So the keyword we're looking for here is and. The mathematical symbol for that is that upside down U-shaped thing. So what that means is you're looking for the places where the values are shared. Sometimes people call this the overlap. You're looking for where the two share values. Because think of like when you're driving and you're in the intersection of two streets, that means you're on the spot where you're on both of the streets at the same time. If you're in the intersection, you're where they cross, right? So that's all we're looking for. So and means intersection. So I know we have this down here as well, but this is a really important idea. It means intersection. So that means your overlap. So you're looking for where they share values, where they share points. So really what it is you just graph each of these separately, these inequalities like we just talked about, and then see where they are overlapping. All right, so we'll do the first one here. So we have x minus y is less than or equal to 4. Okay, so first of all, looking at this solid or dash with less than or equal to is going to be solid included, right? Because we have the equal to. You can write this as an equation then to graph the boundary line. Because this is in standard form, it is kind of a nice way to do the intercepts, x and y intercepts. So that's where you're thinking about putting in 0 for y and 0 for x. If you put in 0 for y, you'd have x minus 0 equals 4. So x would be equal to 4. So you have the 0.40. And then you can put in 0 for x, so 0 minus 4 or minus y equals 4. So negative y equals 4. You'd have to divide by negative 1 then, so y equals negative 4. So you have your intercepts. That's an easy way to be able to graph that one. You can also, like it said, solve for y. So you could have taken this inequality, x minus y is less than or equal to 4, and you could have subtracted your x. And I'm going to show you this because I want you to see what happens. Less than or equal to negative x plus 4. Be careful here, so we need to talk about this. What happens when you divide by a negative? If you divide by a negative, what happens to that inequality? Remember, it reverses. So that would be y is greater than or equal to negative divided by a negative would be positive x, and then positive 4 divided by a negative 1 would be minus 4. So you could use your slope and your y-intercept here then to graph that boundary equation, y equals x minus 4. And be able to graph it that way. So your slope then here would be 1, and your y-intercept would be at negative 4. So you can decide, hey, which way is easier for me, but be careful when you're solving inequalities. If you multiply or divide by a negative, so you multiply or divide by a negative, you have to reverse that inequality. All right, so I'm going to go ahead and graph this one, I think in blue. So I'm going to do this first one in blue. So this first inequality is going to be in blue. So we have our intercepts at x-intercept at 4 and our y-intercept at negative 4. So that was the one way we did it. Or the y-intercept was at negative 4 and the slope was 1. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. Same exact line. So again, it's whichever way you think is easier. We said this is going to be solid because the points on the line were equal to. So we have our solid boundary line. Now comes the shading. Okay, so because I solved it for y, I'm going to have you look at the solve for y version. It says y is greater than. Where do you shade if it's greater than? Well, it's the values above the line. So where the values are greater than the line. Another way, remember, is you can test a point if that's easier. So if I wanted to test a point, 0, 0 is a good candidate because it's above, right? So what if I wanted to test a point instead? If I wasn't 100% confident just looking at the inequality, you put it back in your original. So 0 minus 0, is that less than or equal to 4? Is 0 less than or equal to 4? True or false? Absolutely true. That means I shade in that direction. That ordered pair was a solution. That means every other ordered pair in that region is going to be a solution. So all of these values would be true. Okay, now we're going to do the other line. This one hopefully should be easier. X equals, remember when you only have one value? So we're looking at x equals negative 2. Is that horizontal or vertical? Well, if all the x's are the same and there's no slope number, notice there's no y equals mx plus b here. That means the slope is undefined. That means it's a vertical line at negative 2. So that's a little bit easier to be able to graph. Look at your inequality. There's an equal to again, which means it's solid. So it's going to be a solid line. So this is just going to be a solid vertical line at negative 2. All right. Now this is kind of interesting. For the vertical and horizontal, theoretically it should be easier, but sometimes it's harder. Where are the x's that are bigger than negative 2? What would be a number that makes that true? Is 0 bigger than or equal to negative 2? Let's think of our test point, like the 0, 0. Is that true? Is 0 bigger than negative 2? Well, sure it is. That means you shade in that direction. It's going to go to the right. Right is bigger, right, than negative 2. So all the solutions to the second inequality, I'm doing in green here, would be this. Now the two colors is really nice because remember we want the and now or the overlap. Where do these two graphs share solutions? Well, it's all the places where it's both shaded in green and in blue. So this would be the intersection. Every single ordered pair in that region would be the solution to the system of inequalities. So we're able to show our solution by doing where they overlap. So is it possible that you could graph two that don't overlap at all? Absolutely, and that would mean no solution. All right, let's talk about our last one, union. Union means everything. What you're going to see is a set of inequalities joined by the word or. So when you see or, that means union. That's what we call it mathematically. This is an actual U is the symbol. So if you see a U in between there instead, that means union. It means or. So anything when you see or, that means you shade everything. It means it's either in this one or it's in that one. All of that is going to be the solution. So it's everything. So everything that you shade for each one becomes the complete solution for this entire part. All right, so I'm going to go ahead and do both pieces here. This first one, so 7x minus 3y is less than 18. For this one, when we show and do our graph, I think I'm going to solve it for y so we can use that greater than or less than to help. So I'm going to go ahead and subtract the 7x. So let's do that, and go ahead and pause the video, see if you can solve it for y, and then you can check back with my work. So negative 3y is less than negative 7x plus 18. Remember how we put that x term first so we can see it, that y equals mx plus b? All right, so here we have that same issue we had before. We're dividing by a negative on both sides. That means immediately we're going to reverse that inequality. So y is greater than negative divided by negative, positive 7/3 x, and 18 divided by negative 3 would be negative 6. So just be careful on your solving there. Okay, so we have what of our slope and y-intercept numbers then? Slope, y-intercept. Go ahead and jot those down. Pause if you need to. So the slope, coefficient of the x is 7/3, rise over run, and our y-intercept is negative 6. Is this one going to be solid or dashed? We'll take a look at the inequality. Either one, no equal to, right? Which means this is going to be a dashed line. So I'm going to do this one in green. So we're going to start at negative 6, and then we're going to go up 7. So that would be a positive 1, and then 3 to the right. So we're going up 7 over 3, and it is a dashed line. Okay, now remember we have to do our shading, so it's either going to be above or below. Now remember our final version when we solved it for y here is greater. So that should mean above. And what we mean by above is all the y values that are bigger than where the line would be. Now could we have used 0, 0 as a test point on this one? Absolutely, because it's right there. So if I can want to do that and test 0, 0, remember you always have that option. As long as 0, 0 is not on your line, you can always test a point though. 7 times 0 minus 3 times 0, is that less than 18? Well, 0 minus 0, is that less than 18? Is 0 smaller than 18? Absolutely true. So that's why we shaded above. All right, we have another one of these special case ones. I'll do this one in blue. X is greater than or equal to 3. So first of all, we have an equal to. What does that mean? Solid, so it's going to be a solid, and this is x equals 3. That's a vertical line again, so it's all the values when x is 3. So I'm going to make a vertical line at 3. Ooh, that's always a little scary. All right, now we want the x's that are bigger than that again. So do you remember what way we went when it was greater? Try a point. Put in something. Is 4 greater than or equal to 3? Sure. Where is 4? Over here. If you tried a 0, is 0 greater than or equal to 3? Well, no. So it doesn't go that direction. It goes this way. All the ones that are bigger. All right, now if this were an and, we'd be looking for overlap, and it would just be that little triangle again. But the solution is actually all of the shaded regions together. So it's all the shaded regions, and then whichever solid lines you have. So it's all the shaded regions together makes up all the points that is an or here. So it means any of those. So it's all of these and all of this. So really the only part that isn't part of your solution is this little triangle down there. Everything else is a solution because Or means everything. So we just graph them separately and we put them together on the same graph to show all the points at our solutions. So graphing inequality really comes down to, being able to graph an inequality, no solid or dash with that less than or equal to or just less than or greater than, testing points or solving for y so you know which way to shade, and be able to show all the points at our solutions with that shaded region. And we have our ands, which is overlap, and then intersection, and we have or union, which is everything.